move over one group, now to group 15. And as mentioned before, this group has a name. The pnictogens. And that actually derives from the Greek word for choking, which is kind of interesting. If you have ever smelled ammonia, which I'm sure everybody has, right, that's the instinct you have to do. And so that's where the origin of that name comes. But you don't hear those elements called that all that often. But it's good to know that's what they are. All right, and in this, then, group, we have nitrogen, phosphorus, arsenic, antimony, and bismuth. We start here with nitrogen, which is a gas. Phosphorus is a solid, and so is everybody else on down. Non-metal, metalloid, chemically weak metal, bismuth, or antimony rather. Then bismuth is pretty close to a true metal itself. And so, what are the elements? The most important one of course, is nitrogen. And this is how you find it in nature. It's a diatomic gas. There's plenty of it in the atmosphere. It's the major component of the atmosphere. And if you can recall back to the Lewis structure, you'd have a triple bond. And in this material, that triple bond measures 942 kilojoules per mole, which is really strong. In fact, that's one of the strongest bonds in nature. And so if you go back to the old adage, right, for a chemical reaction, that bonds broken minus bonds formed, if you take the energies for those, that's the energy of the reaction. Right? You're forming a very strong bond that's always going to be favored. And so if you can conduct a reaction, a chemical reaction, for example, that involves dinitrogen, it releases a lot of energy. And we'll see an example of that a little bit later on. Phosphorus despite what you may think, does not mirror the structure of nitrogen in nature. In fact, it's P4. And instead of having a triple bond, what it has is a tetrahedron of phosphorus atoms I drew wrong. There we go. A tetrahedron of phosphorus atoms where each phosphorus is bound to another by a single bond. And this happens to do with the fact that for the third row elements and below, multiple bonding like this isn't as common. It's actually stronger to form three single bonds between phosphorus and a neighbor than it is a triple bond. The triple bond for this molecule is only 481 kilojoules per mole. And this is actually stronger than that. So that's phosphorus itself. Arsenic also comes as As4. Antimony has that structure as well. And then bismuth is actually more of a metal in terms of its crystal structure. So we'll focus primarily on nitrogen and its compounds. And what might be, or what might you think would be, the most important one? Well, there's several, but one of the most common, one of the most important compounds is ammonia, which is a binary compound of nitrogen and hydrogen. Now, it turns out this has a great many uses. In fact, if you're a synthetic organic chemist, you might actually use it as a solvent. If you take a cylinder of ammonia and shake it around, you'll hear something sloshing around inside. That's actually liquid ammonia. Ammonia can be liquefied under pressure or at colder temperatures. And so you can actually take ammonia out of its cylinder, put it in a reaction vessel that's cooled to negative 78 degrees C, which for that all you do is mix dry ice and acetone, and you can do chemistry. So it's actually a very good solvent for synthesis. Its boiling point is negative 35 degrees C. But it's also very industrially important. And it turns out that the main reason for that is actually its use in fertilizer. And so ammonia is produced in large quantities all over the world. In fact, we have a large production facility near Tulsa, here in Oklahoma. And the process that's actually used for this synthesis is actually to prepare it directly from the elements. And the person that did this first was a guy by the name of Fritz Haber, a German scientist. And this occurred in 1908. And so the process that is used is this one, where we take nitrogen as you find it in the environment as N2, hydrogen as you find it in the environment H2, and you combine them together. Now the problem is that it's in equilibrium, and it lies to the left. Which means at room temperature, for example, an appreciable amount of ammonia will not be formed if you mix these two things together in the proper 1-to-3 ratio. You can do this, though, at 1,000 degrees. Which is pretty unreasonable. Right? That's a pretty high temperature. You can achieve it, that's not a problem, but maintaining it, of course, takes a lot of energy. But the ideal conditions that Haber came up with after messing around with this for a while was a temperature of 500 degrees C, which is half of that, so that's not so bad. But the pressure is 200 atmospheres. So again, pretty challenging stuff to do. But if you use these conditions here, 500 degrees C, 200 atmospheres, you can get appreciable amounts of your desired ammonia product out. So the process, this particular part of it, was developed by Haber in 1908. A second scientist was involved also in developing the industrial process for ammonia. This is another German scientist named Karl Bosch, and his contribution came in 1915. And what he did is he designed the plant, the engineering part, if you will, for the processing of ammonia. Where was this done? This was done industrially. A company you may have heard of. BASF, which stands for Badische Alen- und Soda-Fabriken. Aniline is nitrogen-containing compounds, including aniline. Soda is soda ash and things like that. But if you look at the date where this was going on, that coincided with World War I. And so the drive to actually to design a plant like this to produce ammonia wasn't for really good reasons. It was more for nefarious ones, because ammonia can be used for explosives for the German army and the Austro-Hungarian army in particular. So that was the impetus for driving this whole thing together. So what Bosch, with his engineering prowess, and Haber, with his developed process for ammonia production, did was they came up with, together, what's known as the Haber-Bosch process. And this is not as simple as it's going to look. And I've said this before, and it's always true. Right? We can write down chemical reactions on the board or on a piece of paper or whatever, but to carry things out on an industrial scale is often much, much more complex than what you might do in a laboratory setting. So just keep that in mind when we're going through this. And the problem is that nitrogen as N2 and hydrogen as H2 are not found pure in nature. And so you could, if you had the know-how, condense both of these things out of the atmosphere by fractional condensation or something like that. That is a difficult process to do. And so essentially the entire Haber-Bosch process focuses on getting the hydrogen for this in pure form, the first three steps. Nitrogen you can get out of the atmosphere relatively easily. I mean, if you go down to the chemistry stockroom, right, you can see a huge cylinder of liquid nitrogen, stuff like that. So it's actually quite facile to get this. Hydrogen, not so much. And so that's what the process does. So let's look at the steps. Step one has a name. It's called steam reforming. from the name, you might guess there's water involved. As a matter of fact, there is. And the point of this reaction is to generate some hydrogen to make ammonia with. How is it done? Oops. That 3 doesn't go there. This is the reaction that occurs. Methane is combined with water, and that generates carbon monoxide and dihydrogen. Now, this doesn't just happen magically. It's done at 750 degrees C. And the pressure is 4 megapascals. So again, high pressure. And this uses a nickel catalyst. Nickel metal, as a matter of fact, can be used in this. Now, there's a problem with that, though. And that is this nickel catalyst can be poisoned by sulfur. We get nickel sulfide out, the catalyst dies. It doesn't work anymore. That's called catalyst poisoning. And that can actually occur, this very smelly and kind of toxic substance, H2S. But, so what? You don't see that anywhere here. Actually, it's often found along with natural gas, which means natural gas itself is primarily methane, but it has a mixture of stuff other than methane itself, and sometimes that's H2S. You purify the inlet stream of methane with zinc, specifically zinc oxide. And so here's the reaction. You pass the methane stream over a bed of zinc oxide. Zinc is an element that's what's called very thiophilic, which means it has a propensity to bind sulfur. It'll exchange its oxygen with some heat for the sulfur and H2S, and therefore effectively removing it from the stream. So this is sort of a side process that they do. And then you don't have this catalyst poisoning problem anymore. Step 2. Secondary reforming. So all the methane in the first step actually doesn't react. And so you have to control the amount that you put in and all that sort of thing. And so secondary reforming does the following thing. The unreacted methane from step 1 is reacted with oxygen. That produces carbon monoxide, which is an unwanted byproduct, and more hydrogen. And so this is a way to enhance the amount of hydrogen that you're getting, right? Because on industrial processes that are done on a huge scale, bottom line is you want to have an efficient process to maximize your profit. And so having a bunch of methane go to waste would not be practical for this. So that generates more hydrogen from that. There's a second reaction that occurs too. On the side, and that is that methane can react with excess oxygen to give carbon dioxide. But the primary point of doing this is, again, to get more hydrogen out. You do lose some methane in this second reaction shown here. And then the third step is the water-gas shift reaction. And so what this has actually done is, because some of your methane got killed off in the last step, we try to bring up the amount of hydrogen that's formed to be in the 3-to-1 ratio with ammonia. And so this generates more hydrogen, and it's actually done using carbon monoxide produced in step 2. Produce CO2 and more hydrogen. And so again, all three of these steps, the primary thing you're doing is trying to get that 3-to-1 ratio of hydrogen to nitrogen. This is also kind of handy because you can separate this out relatively easily. All you have to do is cool the mixture down to about negative 100 degrees C rather, and you form dry ice. And it's a solid, so you can separate that out of there. And then this process is actually promoted by an iron oxide, chromium oxide mixed metal catalyst. And then finally, again, steps 1, 2, and 3 are to get the 3-to-1 ratio of gases. And the fourth step is actually the actual Haber-Bosch process. The conditions are 300 to 500 degrees C. It changes throughout the process in 15 to 25 megapascals, which is the pressure conditions, which vary. And so that's the Haber-Bosch process. And again, when you put it all together, the first three steps combined with this last one give you about 98% conversion, effectively, from your starting materials to your end products. That's a good conversion if you are working in industry, right? That's what they want to see. So that's the synthesis of ammonia, which is used for a whole bunch of other things. So what is one of them? One of them is nitric acid. You can make a bunch of other compounds, but nitric acid is one of the more important ones. Get to wherever that is in my notes. And so this stuff is a strong acid. Not only is it a strong acid, it is an oxidizer. Because if you look at what's going on, nitrogen in there is in its +5 oxidation state. That's the group oxidation state. Nitrogen, being an electronegative element, doesn't like to be in the formal +5 oxidation state, and so it'll try to get reduced, which means it's the oxidizing agent. And this is produced industrially by the Ostwald process. From ammonia, of course. It's a 3-step process. The first one takes the ammonia gas produced by the Haber-Bosch process and oxidizes it with oxygen. Make NO, nitric oxide, and water. The second step then takes the NO and further oxidizes that. Nitrogen 4 oxide. That's the brown gas that smells really bad, somewhat toxic. If you did the copper cycle general chemistry lab experiment at some point, you saw that produced. And then finally, this stuff is reacted with water, which it does. To make HNO3. That's actually hydrogen nitrate when it's in pure form, but you dissolve it in water, you get nitric acid. And more nitric oxide, which can be funneled back into the second step and reused. And so here, now, we have nitric acid. So what's the big deal with that? Let me get to where I want to be here. that must be used for something too. And as a matter of fact, it is. It's combined with ammonia to make ammonium nitrate. So the main drive for all of this large production of ammonia right now, anyway, and then nitric acid, and then finally this stuff, is for agriculture, fertilization. And so you can't have mass agriculture without this. And the large population explosion at the end of the 19th or the 20th century did coincide with, right, mass agriculture. Can't have the people if you can't feed them. And so again, this is obviously very important. The process to make it is straightforward. This can be done in water. There you have your final product, which you can then get out of the water by evaporation. Or you can do the same hydrolysis too, depending on how your process is. So what is the big deal about this? Well, if you take this material, actually let's do it this way. It's aqueous because that's how it's, and you've seen probably farmers fertilizing their fields. It's done in water. What happens with gentle heating, meaning heat from the sun, right? The heat that just naturally occurs outside, this generates N2O, so that's nitrous oxide, that's laughing gas, the stuff they give you at the dentist, and water. And this is actually the fertilizer. This is the stuff the plants absorb to grow. And so you can imagine how nice of a process this is. You can cart this around as a solid, dissolve it in water, spray it out, and then it just reacts and gives the plants the stuff that they need to grow. Or you can buy it as a solution and do the same thing. But there is one small problem with this, that this isn't the only thermal reaction of ammonium nitrate. The other one is that you start with a solid. Heat this up to high temperature. And you generate water and dinitrogen. Also, a lot of heat. This reaction here, as opposed to this one, is highly exothermic. So why is that the case? This is why. So at the beginning of the lecture, if you can form dinitrogen in a reaction, that's going to make the reaction really exothermic, and that's no exception here. And so this can also be used as an explosive. It can be used for blasting caps, for example, but the historical significance of this one because that applies pretty close to home, especially if you're from the city, that being Oklahoma City. This is the stuff that Timothy McVeigh used in the Oklahoma City bombing in 1995. He detonated a whole bunch of it in a rented truck using diesel fuel as to get this high temperature. And you can see what the results of that were. And so the reason you can use it as an explosive is because, again, that dinitrogen is being generated. So, with all that being said, we'll wrap up this virtual lecture. Again, there'll be a few more of these. I'm not sure how many we're going to do. I'd like to do one per week, and then that would exclude dead week. But we'll pick this up in another lecture. And there will be a quiz posted to Canvas regarding this material. It'll take you, 5-10 minutes to do, just for your attendance record, okay? So we'll see you next time.